I wonder why, bro.
Okay? It's just a penny. Okay? I've got a penny in the bottom. And I'm going to have it on the far side of the cup. Okay? So this is going to be important. Penny's there. It's on the far side of the cup. Okay? Everyone agrees that you can see the penny.
I can't see
I can't see the penny. Okay? It's down the bottom.
I know it's there.
Just trust, okay?
It is a rocket science. Okay. Now, here's what we'll do. Laura, I want you to sit down so you can just see over the top of the cup, but you can't see the penny. Okay? So I want you to have a line of sight where you can see over the top, but you can't see the penny. Okay? You can just barely not see the penny.
Oh,
Are you
barely?
gonna big light?
No way. Bro.
Okay?
So let's go.
Okay. So stay right there. Can you see the penny?
No.
No, you can't see the penny. Okay? Now, I'm going to start adding
Yeah, but I'm
some
gonna
water.
make this like.
Okay?
What do you mean?
I'm gonna blow you up. I'm gonna put a bomb in you. Blow you up.
Now what?
I
No.
can see the penny.
Can you see all of the penny? Can't see all of the penny.
Wait, film it.
Now what?
I still can't see it on
In
the
the cup?
Like from her
Yeah, I
vision.
can.
Put it up
Okay.
to her eye. Her eye.
Her
So,
eye level?
so here's the story.
Next to her.
So she couldn't see the penny, but now she can see the penny. But we didn't move the penny.
The light moved the penny.
The light moved the penny.
Yep.
Okay. Now, you can see the penny, right? Val, you can see the penny. So now we need to figure out why she can see the penny.
Index of refraction.
What about it?
It changes the speed of the
Wait.
Hold on. We need to go over here. Hold on.
Because if it bounces back.
First equation. It's like the snow tire.
It bends
All right. Here's the first one, right?
Life is so simple.
Penny was here. Mara's looking like this, right? She can't see the penny, right? Without the water, she can't see the penny. But what has to happen when you all looked above like this? What allowed you to see the penny? What was the mechanism that allowed you to see the penny?
Light.
What's this? Light.
Light.
Water.
What's the light doing?
Reflecting.
It's hitting the penny and it is
Reflecting.
bouncing back. Okay? That's what's happening.
Which one's her eyeball?
So, this is if you're looking straight down.
Oh, that's the sun.
Okay? Now, when Mara adjusted that line of sight, so she could just barely not see the pennies, right? Air was going through air, then, or the light was trying to go through the air, and then through the cup, and it didn't happen. So then, I added water.
You made a lens.
Okay, now, was the light still bouncing off the penny?
Yes.
Yes, light was still bouncing off the penny. But then it was going up and leaving the water and entering. So which one has a higher index of refraction?
The snow tires.
So in here is like 1.1. What?
So it goes.
In air is 1. So if you go with the snow tire analogy, when it hits this air, what did it do?
Slow down.
That side got slowed up, so what did it do? So light is went like this. So that light started going like this. Okay? Now, your eyeball tries to trace it back to its origin. So when Mara's eye is here and she sees it coming like this, she thinks that penny is right there. Okay? So what allows her to see it is the fact that that light goes, and today you have to keep track of the path of the light. So it's out the penny, into the air, it speeds up, boom, goes like this. But she thinks the penny is there.
Silly Billy.
Okay? All right. Now, next thing. So, turn off, go over to that switch on the wall, and turn off these backlights.
No, I got it.
I believe it. He's gonna break it. I believe it. Oh my god.
Yeah.
Hey,
Push the bottom up. There you go.
There we go.
And now shut off the switch inside the rim. Beautiful, thank you. Okay, so this is what's known as polarizing film. Okay? So if you've ever seen glasses, sunglasses that say they're polarized, okay? All that means is that embedded within the glass, there's these very, very, very small, tiny lines. They're almost like thinner than a human hair. So this is the second piece of polarizing film. Now, if I overlay it like this,
With the green.
okay, what's happening is this is the second piece of polarizing film. So at this point, the first one was allowing light to only go through in a particular direction. So like sorted it out. So that light bulb is producing all these different types of light with all these different directions of its waves. So if I do this, that one has the lines parallel. Okay? So the light's coming through in one direction, the second one is in the same one, so it's like this. So they're lined up, so you can see the light. But if I take the top one and I rotate it 90 degrees, what happens?
Why did it go black?
Stars in the
It goes
middle.
on. Why?
Against the grain.
It's perpendicular.
Yeah, they're perpendicular. So at this point, I have light going through in one direction like this, and then I've got the other one like that.
Okay.
Blocks it off.
Ooh.
Now, if I go in between,
Ooh.
We can find a happy medium.
well, and then if I go completely parallel, you get the bright light.
So are sunglasses like halfway or are they like fully?
So here's how you can check if light that your sunglasses are polarized. If they're actually polarized. So when light skips off, especially like a shiny floor, that light basically is only going in one direction, kind of like this. Okay? So then if you take your sunglasses and you rotate them as that light's coming through, bouncing off the floor, if they're actually polarized, it should get darker.
Yep.
Okay?
Toasties.
All right. So, your basic protractor.
Oh dear.
Put it up there. Not so cool. I know, disappointing.
Wait.
However,
Yo.
You are
if I
my
do
son.
this though,
Mr. Berg, how are you doing that?
Mr. Berg, what are you doing?
He's a leprechaun. There's a pot of gold.
Mr.
So,
Berg,
here's what's happening.
are you a magician?
No. So that material that makes up the protractor is going optically active. So what it does is it twists the light as it goes through it. Okay, you can't tell it. So what's happening? If you normally look at it, you can't tell this. So the light's coming through the first polarizing lens. Only certain bands of light are allowed to go through that first polarizing lens. It interacts with the protractor and it bends it. But then when I put the second one on there, now because that light is getting twisted, what happens is that the second one then sorts it out and only allows another set of different colors to go through. Now, protractor. So this is corn syrup.
Bottle of gin.
Syrup?
Corn syrup. That's all it is corn syrup. Looks completely clear, right? Nothing impressive.
Kinda.
But,
Yo.
There are things
Mr. Berg, are
inside.
you a warlock?
yep. So what that tells me
They are.
is that corn syrup is also optically active. So, however, the protractor, what it does to light, is the same thing the corn syrup does to light. Because they're both optically active, and as that light goes through the particles that make that up,
Yo.
it gets twisted. And then you end up with
Disco ball.
a disco ball. Okay. All right.
I'm scared.
Mr. Berg, did you secretly go to Hogwarts?
Yeah, that's it.
Is that what we're pulling away from this?
So,
Nathan, he's a magician.
Mark, come here.
He's a wizard.
Or somebody come here.
You're a wizard.
Coming?
Right
All right. Okay. So we got green light, right?
Yeah.
Okay.
Red light.
Okay.
Hold it
And
right.
then I've got
Can I hold one?
white light. Okay. And then I've got
Blue.
Blue.
blue light.
Yo.
Okay. So, and then I've got
Red?
red light. Okay? Now, if I merge the blue and the red.
Purple.
Purple.
Yes,
Purple.
Now, if we move the green and the red.
Orange.
A little bit closer.
Orange.
I literally can't see.
Okay?
Yo!
You get some orange. Okay? Now, what I'm going to do is we're going to move all three of them together.
White. It's gonna be white. It's gonna be white.
And you get pretty much white light. So what that tells you is that white light is made up of what?
All of them.
So, because if I do white light, okay, so this is why LED lights are white lights, because of the fact that for us to see anything, you have to have you have to have all three of this. So this light that you see coming out looks like white light, but it's actually a combination of all the colors.
Wait, Bird.
Okay.
Bird. One time I dropped a piece of water on my phone and I saw green, red, and blue pixels.
Okay. I don't know where you want to go with
It's making all the colors.
Yeah,
Okay.
it's
All
already
right.
got it.
Okay. Get back. All right. Now,
We're
back over
learning
here.
so much.
Hey, your phone will have justice.
Watch out, watch out, watch out.
Mara's not done yet.
Okay.
Where's it burnt at?
Okay. So I've got razor. Razor. Two. Okay.
No.
And all I did was I put a little bit of milk in there. Okay.
Yeah, I can't.
So that's allowing that to
Take
scatter,
it, bro.
because if I shine this on the ceiling, you can't see the laser beam. Why?
Nothing
Because it's traveling, but it's traveling through the air, and there's
Yo,
nothing
Nathan, it
for it to
comes
bounce
with
off
it,
of. So even if I shine it like kind of like through just that clear part like this,
You can't
okay?
see it.
Get on the
where you
ground,
can't see
Mr.
it.
President.
Now, I need you to move so I can move the. I need to aim for that light. Okay.
Gavin.
Okay.
Split the
Now,
sea.
So here's what I'm going to do. I'm going to shine this light as best I can on that metal frame. Okay? See it's on that metal frame over there?
Yeah.
Okay. Now, what I'm going to do is I'm going to lower this down, trying to maintain that same path, but then I'm going to make it go through the water.
Yo.
Wait, that's water?
Okay? So when it goes through that water, what happens?
It's being moved over.
Spreads out.
Well, which way does it shift it?
Left.
Left.
Just to the left. Why?
Because refraction.
So it goes through. Here's it goes through like this. It hits the angle like this. What happens?
Bent.
One side
Goes faster.
one side slows down when it hits the water and it gets bent, right?
Yeah.
Okay, gets bent, goes over. That's why that line shifts. Now, so if I go from air into the water, so this is kind of cool because this very much shows how that's slowing down. So I've got this, right? So if I'm over here, notice where it's hitting,
Straight.
okay?
Right there.
But then I move it into the water.
In one side, theta one.
Yeah, and so it goes from out there hitting to here. Because it hits that water, what's it going to do?
Refract.
Refract, it's going to slow down, right? It's going to hit that boom, it's going to slow down. Now, this one, I'm going to shine it through the water, and I'm going to have it go into the air, okay? So, I'm going to start off fairly shallow, but now, if you notice as I go steeper, what happens?
Or why is it on the ceiling?
Okay?
Oh, I'm not even looking at the ceiling.
Where at?
Yo, it's over there. Whoa.
Wait, why is
He's
he
hacking.
Oh, it's my mic.
Berg, I thought it'd be over here, man.
Okay.
You were bouncing.
So,
Life hack by IRL,
here's what I want you to see. This is what's known as total internal refraction. So, but there's a critical angle, and we'll do the geometry in just a second.
Oh God, I got it.
So, if I'm too shallow, okay, then it goes through the water and hits the air. So if it goes from the water into the air, when it goes into the air, what's it going to do? Speed up or slow down?
Speed up.
Speed up.
Speed up, right? So, but if I change this enough, what happens is that this gets bent and it comes back down. Now, I've got a little bit of that dot showing back up there.
Because it goes back.
That means because some of that light is being reflected back that way. So if I put my hand here,
It's on your hand.
yo.
Why does it
that
do
kind of like
that?
how whenever we draw that one like pizza line and then it goes like down and then all the way out? Is that
Yes.
kind of what that is?
Similar type idea. Okay? So some of that light is staying in here, but some of that light is also getting reflected back. So this would be more like a concave lens, where that light tries to spread out, but some of it returns back and forms that image. That's what's happening here. So as that light is going out, okay, a lot of it stays in here, but some of that gets bounced back, and that's why that's showing up there. So not all of it is staying within this, but here's what I want you to see. And you'll see the math later on. This only works if you're going from a more optically dense medium into a less optically dense medium. Okay? So what happens is that I can reach that point, you can have two things happen. One, where it just goes parallel with it, okay? Because it just doesn't know what to do. It doesn't know whether to go out, it doesn't know whether to stay in. I don't know what to do. But if I go steeper than that, then you get this total internal reflection. Got it? Good? Grand? Stop that. Let's go to the fish tank.